Good afternoon, all. So, my name is Vishwas Singh, working as assistant professor in Department of ECE, Vidyavardhaka College of Engineering, Mysuru. So today we'll be looking at GATE 2021. For GATE 2021, we'll be looking at communication system subject. Okay. So a brief about GATE 2021. So its organizing institute is IIT Bombay. So in this session, we'll be looking at various concepts. Before that, we'll be analyzing the weightage. We'll be seeing the preferred books, topics which are important for the GATE 2021, and we'll be seeing some of the previous year's questions. So coming to weightage analysis for communication systems. So weightage for communication systems in 2020 was allotted 11 marks, and in 2019 we had 12 questions or 12 marks, and in 2018 it had been given for 10 marks. So based on the marks, we can say that it is a very important subject for GATE. So some of the preferred books is Principles of Communication Systems by Donald Schilling. So and Communication Systems by Simon Hyken. Communication Systems Engineering by Proakis and Masood Salehi. And for the random processes part, we have probability, random variables, and random signal principles by Peyton Z. Peebles. Okay. Since it is very nearer, since you have only a month of time for preparation of GATE, you could also go with any book which you have studied in your UG courses. So next, so the topics which are very important for communication systems in GATE 2021 is one is the autocorrelation, and power spectral density, and properties of white noise. So this forms the very important concepts, because recently with the trend of GATE, we have seen that most questions are asked from this part: random processes, that is autocorrelation, power spectral density, white noise, and filtering of random signals through LTI systems. So these concepts forms the major part in the recent GATE question papers. Okay, and in many of the other exams too, these are the questions which are scoring. Okay, so do not neglect this part. So many of the students feel it is very difficult and leave these questions, but if you know some of the basic formulas or basic concepts, you could actually clear or get good marks using these concepts. And these forms the scoring. So other than this, we also have analog communications. In that, we have amplitude modulation and demodulation schemes. In amplitude modulation and demodulation schemes, we have amplitude modulation, DSBSC, SSB, and VSB. For angle modulation and demodulation, phase modulation and frequency modulation are the concepts which have been asked in the recent years. So earlier papers were having more questions on amplitude modulation and demodulation, but in the recent years, more weightage is given towards angle modulation and demodulation. So phase modulation and frequency modulation schemes and formulas for those, if you go through that, okay, you will be having at least a one question based on that. So other topics are spectra of AM and FM, super heterodyne receivers, and we also have circuits for analog communications, which is followed by information theory, in that entropy, mutual information, and channel capacity theorem. So if we go on prioritizing the concepts, the information theory will have at least a question in GATE. So do not leave that part too, because as we have seen, students are missing some of the concepts in information theory and hence leaving the questions. So it's better you go through this. One is the angle modulation and demodulation. The other is random processes and information theory, which are very important, I would say. Coming to the digital communication part, we have PCM, DPCM, and digital modulation schemes with amplitude, phase, and frequency shift keying, QAM and MAP, and ML decoding. QAM is quadrature amplitude modulation, MAP, and ML. Okay, maximum a priori and maximum likelihood decoding. Okay, then we have match filter receivers. Then calculation of bandwidth, SNR, and BER for digital modulation schemes. Fundamentals of error correction and Hamming codes. Okay, we could say these are the next to be prioritized. Okay, get good in these topics and you will sure have at least a question from these topics. So then we have, sometimes you may be asked with timing and frequency synchronization, intersymbol interference and its mitigation, and basics of TDMA, FDMA, and CDMA. So I'm not saying that we have to leave these topics, but having a good grip on the topics mentioned will get you to score the marks and get you good ranks. So coming to analog communication. So first we'll deal with some of the basic concepts and then we'll move on to solving some previous year questions. So talking about communication, so we'll have a model of communication. So with the model of communication, we'll have an input signal, then which is applied to a input transducer, okay? Which is then converted to electrical signals and some processing is involved. Okay. After processing, it is sent through a transmitter. Okay. So from the transmitter, it is actually fed to the channel, right, where your noise is added. So from the channel, we are going to decode it. Before decoding, you would have to receive the signal, right? So receiver will have and then after receiving, we are going to do some processing using demodulator and decoder. And then we are feeding it to the output transducer. To get our output signal. So this forms the model of model of communication system. So a communication system we can model it using this block diagram. So we have input signal, which is then converted to the electrical signal using a transducer. Then we are going to do some processing to it and feed it to the transmitter. So this transmitter converts our baseband signal to the required band, and then that is fed to the channel. So in channel, we are going to deal with white Gaussian noise. Okay, so which is added, which is just additive in nature. So we are going to deal only with the additive white Gaussian noise, which would be helpful for dealing with the systems in communication. Then from the channel, we are going to receive it using a receiver and then feeding it to a output transducer to get the output. So this is the model of our communication system. So after studying about the model, we will see about the modes of communication. So what are the modes of communication? If we say it is, one is broadcasting, the second one is point to point. Okay. So these are the two modes of communication which will see in large. Okay, it is basically broadcast means you have one to many, like the radio or television, and point to point means one to one, like telephones. So we have two modes of communication. So after modes of communication, what we need to know is the techniques of communication. So seeing the techniques, we have again two schemes. One is the baseband communication, and another one is the band pass communication. So baseband and band pass are the two techniques which are basically used in the communication systems. So to talk about the baseband communications, it is low frequency, it is less powerful, and it undergoes more attenuation, and the distance with which we can communicate is very less. So we can say it as local area communication or localized. So using the baseband communication technique, so we could only talk or communicate for very less distances due to problems which we face. That is, it is less powerful and more attenuation. So the other technique is the band pass communication, where this is a high frequency, modulated using carrier, and it can support long distances. So majorly we are concerned more with the bandpass communication. After this, so basically our signal which we use like voice or image is a very low frequency, right? So it is 3 to 3 kilohertz is our voice. Sorry, 300 to 3 kilohertz. So if we have to transmit this directly, it would be affected with the noise. So what we have to do, we have to shift this to the higher frequency range. So the process with which we do this is called as modulation. So modulation scheme is basically you have your message signal or voice signal, M of t, let me call it, which is of low frequency, and it is multiplied with the carrier frequency, let me call it C of t, which is of high frequency, to obtain the transmitting signal or modulated signal, which is S of t. This is high frequency again. Okay, so why is modulation needed? Means because we can reduce the interference, multiplexing is possible, needs of modulation, reduce interference, multiplexing is possible, and the major thing is we can reduce the height of the antenna. So the next one is we can improve the SNR, signal to noise ratio is improved, and long distance communication is possible. So these are some of the advantages of modulating a signal. So modulation process, okay, modulation scheme, we can classify it mainly into two categories. One is the continuous wave modulation and another is digital wave modulation. Okay, in continuous wave modulation, we can have amplitude modulation and angle modulation. Then we can have pulse modulations. And in digital modulation schemes, we can have ASK, PSK, and FSK. So to attempt the problems in communication systems, you need to know some of the basics of Fourier transforms. That is the mathematical preliminaries which is required for applying the concepts studied in analog communication. So the first is, if we have a signal x of t, its Fourier transform is x of f, where x of f is integral from minus infinity to infinity x of t e to the power minus j 2 pi ft dt. Okay, so if we have some waveform like this, just a random waveform, so we can have a spectrum somewhat like this, which is obtained. Okay, so when you have your spectrum like this, you'll have, say, here FH and FL. So bandwidth is FH. So this is the basic definition of bandwidth. So more narrow is the bandwidth, less noise enters. Okay. If bandwidth is very low, lesser is the noise, and bandwidth of the channel must be greater than the bandwidth of the signal. Okay, this is the requirements for communication to happen. And the bandwidth, we can represent it as a BW or B. It is 1 by pulse width. Next, the concept which we need to know is the rectangular function. So it can be represented like this. So you have from minus pi by 2 to pi by 2, and amplitude, let us say A. Okay, so when we apply Fourier transform to it, we'll obtain a sync pulse. We'll obtain a sync pulse, that is AT sync of FT, where sync of x is equal to sine pi x by pi x. So after this, we also need to know a property of Fourier transforms, that is the shifting property, x of t cos 2 pi fct or 2 pi ft. Its Fourier transform, when we apply that, x of f minus fc plus x of f plus fc whole divided by 2. So these are some of the concepts which we have to know, right, before entering into the analog communication. So if you know these concepts very well, okay, then we can analyze the questions and we can answer easily. So in analog communication, we have amplitude modulation. So its general form representation is S of t is equal to C of t into M of t, we can say. And S of t is equal to AC into 1 plus Ka M of t cos 2 pi fct, where AC is the amplitude of the carrier, cos 2 pi fct is my carrier signal, Ka is the amplitude sensitivity, and M of t is the message signal. So this is the general form representation. M of t, if it is less than 1, we can say it is undermodulated. And Ka M of t greater than 1, we can say it is overmodulated. So this is very much preferred method because undermodulated gives us the phase reversals. So this is the problem in undermodulation. So coming to frequency domain representation, S of f is equal to AC by 2 delta of f minus fc plus delta of f plus fc plus AC KA by 2 M of F minus FC plus M of F plus FC. So this is the frequency representation. So here the bandwidth is BW is equal to 2W, where W is the frequency of the message signal. So we can have S of T is the carrier plus USB plus LSB. So please note this concept. So whenever you are given an equation S of T, and you have to note the terms which are which. Okay, if you try to recognize these terms, you can easily solve the problems. So coming to the specific case of single tone modulation, M of T as AM cos 2 pi FMT. We can have Ka into AM as the modulation index as mu, and this is a dimensionless quantity. Then we have to know that AM is equal to Vmax minus Vmin by 2, and AC is equal to Vmax plus Vmin by 2, and hence mu is equal to AM by 2. Sorry, AM by AC. AM by AC is the modulation index. So if we know these concepts, we can attempt the AM based questions. So another formula which we need to know is mu is equal to AM by AC, which is equal to Vmax minus Vmin by Vmax plus Vmin. So this is got by this, we have this modulated signal, right? So using this, we have obtained. So we have something like this, right? So using this, we have Vmax, Vmin. Okay. This is how we have got that. Then we have to know some of the power relations. P of T is equal to PC plus PUSB plus PLSB, where PC is carrier power, AC square by 2, and PSB, I can say sideband power, which is mu square AC square by 8. So if we have known, if we remember these two things, we can answer the questions. So if they ask you for a specific R, we'll have a R term here. Okay, just remember this. Then we have the modulation efficiency eta is equal to mu square by 2 plus mu square. So that is about AM. Then coming to the next part, that is modulation and demodulation. We are going to do with square law modulation. Square law modulation, this is a bit important concept because you have been asked questions based on this. So you have a M of T message signal that you are going to pass it through a product modulator, and you are going to pass it through a non-linear device. Okay, non-linear device, and then pass it through a band pass filter to get the output. So here we have to note if this is V1 and this is V2. We have been given V1 is equal to M of T plus cos 2 pi FCT into AC. and V2 is AV1 plus BV1 square. That's why we have a nonlinear division here. So based on this, we would have to find out the ratio K, which is 2B by A. So remember, this K is only for when you have V2 as AV1 plus BV1 square. If it is in that form, you can directly take it. K is equal to 2B by A. Then coming to demodulation, we can have a square law demodulator or envelope detector or synchronous detector. So envelope detector is the mostly asked question. Okay, envelope detector is mostly used. So for envelope detector, we must have 1 by FC must be less than RC, which must be less than 1 by FM. So this condition must be met to actually demodulate the signal. And we have to note that envelope detector is only good until mu is less than 1. Okay. So that's about AM. Then we'll have DSPSC. Again, we'll have relations for it. In DSPSC, you just need to know PT is equal to 3 by 2 PC for mu is equal to 1. So you will have questions based on the power in DSPSC. Okay, and again SSPSC, you'll have that. So you would have to calculate power saving when compared with DSPSC and SSB. So these are some of the concepts which we need to know. And generation of DSPSC is through balance modulator or product modulator and ring modulator. And demodulation is through a nonlinear device, okay, or coherent detector. So again, we'll not go in detail for analog modulation. We'll have a analog modulation, angle modulation. In that, we'll have S of t is equal to AC cos of 2 pi FCT plus theta. This is for change in FC would give us the FM, and change in theta would give us the PM, which is the phase modulated signal. Okay. Some of the relations which we need to remember is delta F is equal to KF M of t max, and theta of t is equal to 2 pi integral Fi dt, where Fi is the instantaneous frequency. So for narrowband, we have two types of frequency modulated signals. One is the narrowband FM and wideband FM. Narrowband FM is when beta is less than 1, and wideband FM, beta is greater than 1. So main formula which would be used in your problems is BW bandwidth is equal to 2 into beta plus 1 into FM. This is very important. This is the Carson's rule. So to retrieve the signal, you have to pass through a band pass filter whose cutoff frequency is beta plus 1 into FM. Okay. And we also have the relation PW is equal to 2 delta F plus 2 FM. So these are some of the things which we need to remember. If we know these things, we can actually answer easily the analog modulation schemes part. Okay. So then we have noise. So we have thermal noise, white noise, short noise, transition time noise, and give you a noise characteristic. Say if they say it is a one-sided, it is like this and not. This is the PSD. This is the PSD, power spectral density, and if they given it as a double-sided noise, it is N0 by 2 here, like this. Okay, so based on these two, you would have to analyze and solve. Okay, we'll see some of the problems now, which have been asked in previous years. So the first question, for the modulated signal, x of t is equal to m of t cos 2 pi fct. The message signal m of t is equal to 4 cos 1000 pi t. And the carrier frequency is fc, which is 1 megahertz. And the signal x of t is passed through a demodulator. It is given in the figure. The output of the demodulator we have to write. What is y of t? We have to write. Okay. So do not directly go into the questions. First, read the question. So when you read the question and analyze it, okay, you will actually get the answers very fast. So for example, they have given here, they have given you the transfer function here. Its cutoff frequency is minus 510 to 510, right? So since it is a low pass filter with cutoff frequency 510 hertz, okay, we must know that it is less than 540, sorry, 510. Okay, so the signal which is coming out of this would have a frequency component which is less than 510. But please make a note, what is 2 pi of 510? So it is around 1 megahertz. So nearly around this range, you'll get the answer. Okay, nearer to this. You have to note that. So now, what is that they have given? Here they have given x of t. X of t we have m of t cos 2 pi fct, and m of t they have given us 4 cos 1000 pi t. Right? So they are multiplying it. So we'll get x of t into cos 2 pi into fc plus 40 t. Okay, again they have given x of t is what? X of t is m of t into cos 2 pi fct. So just put that m of t into cos 2 pi fct 2 pi into f, right? So this is of the form cos A, cos B. So cos A, cos B, basic trigonometric identities. We need to remember that. Cos A, cos B is 1 by 2 cos of A plus B plus cos of A minus B. Right? So we can write this as m of t by 2 cos 2 pi 2 fc plus 40 into t plus cos of 2 pi into 40 t. Why? Because fc plus fc, 2fc, fc minus fc, 0. So you'll have only the constant term which is 40. So this will get. Okay. So now, again, we have m of t is equal to 4 cos 1000 pi t. So I will write this as m of t is equal to 4 cos 2 pi into 500 t. We can consider it like this, right? So we have multiplied it in here again. So multiplying 4 by 2. 4 by 2 is 2. So I'll adjust it in here. So we'll have 2 cos 500 pi t into cos of 2 pi f c plus 40 t. We can write it as cos of 2 pi into 2 f c plus 540 t plus cos of 2 pi into 2 f c minus 460 t. Then other two terms will have cos of 2 pi into 540 t plus cos of 2 pi into 460 t. Right? So now, please observe, we'll get the answer here itself, but you need to make small change. Okay? So this is my given, or after this is the point where I'll get this signal. I have these components. So this FC is 1 megahertz, which is very high. It does not pass through this low pass filter. So this is gone. This is also gone. And next, this is 540, right? So this is also gone because we have 510. And only this term will remain. So only this term, that is cos of 2 pi into 460 t will remain. So don't go on taking this as 460 because please see here you don't have 2 pi. So 2 pi into 460 you have got cos of 920 t. Okay, cos of 920 t. Please don't make such small mistakes. Okay, therefore the answer is B, which is cos of 920 pi t. So we'll see the next question. So this is based on the random variable. We have been given a random variable y, which is integral from minus infinity to infinity, w of t, phi of t dt. And they have given phi of t as 1 from t between 5 to 7. So looking at this, you might get fear, but don't worry, it is very small. So SW of f, they have given as 3 watts per hertz. So this is the power spectral density of the noise which they have given. Okay, and we have to find the variance of y, which is where of y we can see. Okay. So we need to remember the relation here. SW of f, if they have given, okay, if they have given that, then we can get, say if it is say n, okay, then we say the autocorrelation function of such a noise is n delta of t. Remember this relation? Autocorrelation function of the noise is equal to n delta of t, where n is the SW of f, which is the power spectral density. Okay. So variance, we know that variance of y by mathematical preliminaries is expectation of y square minus expectation of y the whole square. Okay, expectation of y square minus expectation of y the whole square. So we have been given y is equal to integral from minus infinity to infinity w of t phi of t dt, where w of t is the noise. So expectation of y, right? Expectation of y, I can write it as expectation of w of t, which is the area under per spectral density at f is equal to 0, which is 0. So therefore we have got E of y is equal to 0. So this term is gone. Now we have to find E of y square. E of y square. I can write this as E of y into y. Okay. So if we solve for this, substitute for y, okay, we'll get something as integral from minus infinity to infinity, double integral 3 delta of t1 minus t2 phi of t1 into phi of t2 dt1 into dt2. So this is only valid when t1 is equal to t2 is equal to t. Okay. So we can write this as 3 into integral from minus infinity to infinity delta of 0 dt integral from minus infinity to infinity pi square of t dt. Okay, where delta of 0, 3 into delta of 0, we have this as 3 into 1. We can write this as that. And integral from minus infinity to infinity phi square of t dt, we can write it as the energy of phi of t, right? As we know that energy is equal to integral from minus infinity to infinity x of x square of t, okay, dt. So based on this, they have given us phi of t as 1 from 5 to 7, which is 7 minus 5, which is 2. So we can write that as 3 into 1 into 2, which is equal to 6. So the answer is 6 for this. So this is the second problem, which is based on the random variables. So here we need to note some of the concepts, that is SW of f, and if it is n, I could say the autocorrelation function as n delta of t. Okay, we need to remember this. If we remember this, we could solve it easily. So the next question is the baseband signal m of t is shown in the figure. It is phase modulated to generate a PM signal. Phi of t is equal to cos 2 pi fct plus k into m of t. The time t on the axis is in milliseconds. Okay, is in milliseconds. The carrier frequency is 50 kilohertz and k is equal to 10 pi. The ratio of minimum instantaneous frequency in kilohertz to the maximum instantaneous frequency in kilohertz rounded off to 2 decimal places we want. Okay, so what they have asked is Fi of minimum by Fi of maximum we have to calculate this ratio up to 2 decimal places. Please note, this is a numerical question. So you would not have any options here. So you would have to actually calculate it. Okay. So using the instantaneous frequency, Fi, we know that for PM signal, I could write this as 1 by 2 pi d theta of t by dt, which is equal to Fc plus k by 2 pi dm of t by dt. Okay, so they have given k as phi, k by 2 pi as phi. So we can write it as, since this is a derivative, okay, derivative of this function will have a rectangular pulse like this. Okay, it is somewhat like this. We'll get it. Here t is in milliseconds. So when we differentiate it, when we calculate the values, we'll have 2000 in here and minus 1000 in here. Okay, the 0, 1, 2, 3. So 0, 3, then we have 4, then we have 6. This is where our transitions lie. Okay, so Fi minimum is they have given as Fc as 50 kilohertz. So the minimum frequency is instantaneous frequency is 50k minus pi into 1000, which is around 45 kilohertz. Max is 50k plus 5 into 2000, which is 60 kilohertz. So Fi min by Fi max, we have 45 by 60, which is equal to 0.75. Okay, this is up to 2 decimal places. Okay. Then the fourth question. The fourth question. A voice signal M of t is in frequency range of 5 kilohertz to 15 kilohertz. The signal is amplitude modulated. This is based on the amplitude modulation. Okay. To generate an AM signal, f of t is equal to a into 1 plus m of t cos 2 pi fct, where fc is 600 kilohertz. The AM signal is to be digitized and archived. Okay. This is done by first sampling f of t at 1.2 times the Nyquist frequency. Okay. And then quantizing each sample using a 256 level quantizer. So we have combination of concepts in here. So one is the amplitude modulation. Next, we have conversion to digital signal, that is the Nyquist frequency. We have quantizing. Okay, we have the combination of all these concepts. So you need to have a recall of all those. So how to approach this problem is what we have to find. We have to find the rate. Find the rate. Okay, find the rate in megabits per second of the stream of coded bits. We have to find RB. Okay, we have to find RB. Actually, this is a simple problem if you try to analyze it. Okay, we'll see now. So the first thing, what they have given, the voice signal m of t is in the frequency range 5 kilohertz to 15 kilohertz. Okay, so I could represent that as like this, right? So I have two sides. One is the positive side, one is the negative side. This is minus 15, this is minus 5, this is 5, and this is 15. Let us assume that is in kilohertz. Okay. So this is our m of t. So to calculate the bandwidth, right, for RB, we need what? We have this relation n into fs. Okay, n is got by this number of levels, and to calculate the sampling frequency, right, we need to get to know the highest frequency component. Okay, since this is amplitude modulated, okay, this is amplitude modulated, so the amplitude modulated signal, I can represent it like this. So this is fc, it is at 600 kilohertz. So see, from this is 600, and you have 605 in here, 615 in here, and we'll have 595 and 585. Okay, so the highest frequency component is 615. So this is what we'll have to use it for sampling frequency. So rate, we have 2 into 615, which would give me 1230 kilohertz, or 1.23 megahertz. Okay, so here it is not directly at the Nyquist frequency. You have to see that it is 1.2 times the Nyquist frequency, right? So fs is 1.2 into 1.23, which is around 1.476 megahertz. Okay, so fs is 1.476 megahertz. Now next we need to calculate the number of levels. The number of levels n. So they have given it as 256. So n we can calculate as log to base 2 of 256, which is 8. Okay, so last RB is equal to NFS, we can write, which is multiplying this 1.476 into 8. So that would be around approximately RB is 11.81 megabits per second. Okay, this is our answer. So like this, you would have to analyze, right? If you have to analyze, you can answer the problems easily. So try drawing this for every problem, get a practice of it. You can answer it well. So yeah, all the best. So thank you. The next part about information theory would be taken by Professor DJ Chaithanya Madam. Thank you all.
Welcome to today's session. Myself Chaithanya, working as assistant professor in the Department of ECE. In today's session, I'll be discussing regarding the ITC related questions appeared in last GATE exam. Here the first question is, which one of the following graph shows the Shannon capacity in bits of a memoryless binary symmetric channel with crossover probability P? This question they might ask you for 1 mark. Generally, we are going to write for a memory binary symmetric channel the channel capacity which is given by C, which is equal to 1 minus h of P, where P stands for crossover probability. Here h of P, which is equal to P log 2 1 by P plus 1 minus P log 2 1 divided by 1 plus P. As I told you, P stands for crossover probability, where C is the channel capacity. Here C, which is equal to 1 plus P log 2P plus 1 minus P log 2 1 minus P. Here the channel capacity is nothing but the maximum amount of information which is carried by the channel at the condition when P is equal to 0, C which will be equal to 1. At the condition when P is equal to 1, C is equal to 1. At P equal 1 by 2, so C, that is the channel capacity, which will be equal to 0. Based on these points, I'm going to plot the capacity of a BSC as a function of the error probability. 1, 0, 1. This is how we are going to plot the graph for these three values: C equal 1, C equal 1, C equal 0. Therefore, my answer is in this C. So coming to the second part of the second question. So here a communication channel with AWGN operating at a signal to noise ratio where SNR, which is greater than 1, and bandwidth, which is indicated by B, which has having a capacity C1. Here the question is, if SNR is doubled by keeping a B constant, what is the resulting capacity for C2? For this, we need to apply the condition. Here the condition, given condition is when SNR, when it is greater than 1. Generally, the channel capacity which is given by C1, which is equal to B log 2, 1 plus S by N, where C1, which is nearer equal to B log 2 S by N. In the question, they gave you when SRN is doubled. When SRN is doubled, the condition is C, which is nearer to B log 2S divided by N. After simplifying this, B log 2 plus B log 2 S by N. Again, after simplifying, B log 2 S by N plus where log 2 which will be equal to B. So my answer is C1 plus B, where C1, which is equal to B log 2 S by N. So my answer is coming to this, they gave you C2 which is equal to 2C1, C2 which is equal to C1 plus B, C2 which is equal to nearer to C1 plus 2B, C2 which is nearer to C1 plus 0.3B. After simplifying of this, we got the answer as C2 which is equal to C1 plus B. This is my answer. Coming to the next question. So this question, they might ask you for 1 mark. Here they gave the question like a source alphabet which consists of what? N symbols with the probability of the first 2 symbols being the same. Here a source encoder which is going to increases the probability of the first symbol which is going to increase the probability by a small amount. Then it is going to decrease of the second. After encoding, what is the entropy of the source? So the answer is, so the multiple choice they gave you like increases, remains the same, increases only if n equal to decreases. Let us discuss the question. Generally, the entropy of a random variable x which is defined by h of x which is equal to minus summation x p of x log 2 p of x. Let us consider a simple case where x can take two values 1 and 0 with probability p and 1 minus p respectively. The condition is when x is equal to 1, the probability will be equal to p. Okay, when the condition is 0, then the probability is 1 minus p. Then the entropy of x is written as h of x which is equal to minus p log 2p minus 1 minus p log 2 1 minus p. So by using this equation, we can plot the entropy versus the probability p, which is shown as, you can observe over here. Here we are going to plot the probability versus the entropy. Here the plot of entropy versus the probability, which is showing the graph. By seeing this graph and the equations, we can see that the entropy is maximum. The entropy is maximum when the condition p is equal to 1 by 2, and for other values of p, the entropy is lower. You can observe when the condition p is 1 by 2, then only it is maximum, and for other values of p, the entropy is lower. Then the entropy which is going to become 0 when the condition p equal 0 or 1. The entropy becomes 0 when p is equal 0 or 1. That is when the value of x becomes deterministic. Here we can extend this to source with more than 2 symbols. That is when probability of one of the symbols become more higher than the other, uncertainly it might decrease, and hence entropy also decreases. So my answer is decreases. Here when the uncertainty decreases, my entropy also decreases. Therefore my answer is decreases. So next question is, the probability of the 5 possible outcomes of an experiment which are given as p of x1 1 by 2, p of x2 1 by 4, P of x3 1 by 8, P of x4 1 by 16, probability of x5 is equal to 1 by 6. If there are 16 outcomes per second, then what is the rate of information would be equal to? They gave the 4 options, that is 25 bits per second, 30 bits per second, 35 bits per second, and 40 bits per second. Generally, we are going to write the entropy of the system is h of x, which is equal to summation I, which is equal to 1 to 5 p of xi log to 1 by p of xi bits per symbol. Or we can write it as h of x 1 by 2 log 2 1 by 4 log 4 to the base 2 plus 1 by 8 log 8 to the base 2 plus 1 by 16 log 16 to the base 2 plus 1 by 16 log 16 to the base 2. So either we can write in this way or in this way. So after simplifying this equation number 1, I'll be getting 1 by 2 plus 2 by 4 plus 3 by 8 plus 4 by 16. Therefore, answer is 15 by 8. This is nothing but 15 by 8, which is equal to 1.875 bits per outcome. Now, the rate of outcome, which is equal to R, which is equal to 16 outcomes per second. In the given value, in the given question, they gave you the R, which is equal to 16 outcomes per second. It is nothing but the rate of outcome. Generally, if you want to find the rate of information, which is indicated by R, which is equal to R into h of x. Already we know the value R, which is equal to 6. Already they gave you in the question, where h of x, which is equal to what? 15 by 8. Substitute over here. So after multiplying 16 into 15 by 8, I'll be getting 13 bits per second. So my answer is 30 bits per second. In the question, in the multiple choice, they gave you 25 bits per second, 30 bits per second, 35 bits per second, and 40 bits per second. So my answer is, after simplifying the probabilities of the 5 possible outcomes, I'll be getting 30 bits per second. So next question is, a fail is tossed repeatedly until a head appears for the let L be the number of tosses in order to get this first head, and then they told you to find the entropy h of L in bits. They told you to find the entropy of h of L in bits. This question they might ask you for 2 marks. This question they might ask you for 2 marks. By simplifying the question, suppose if one toss is required, in order to get the first head, then the probability which will be equal to 1 by 2. Suppose if one toss is required in order to get the first head, then the probability which is equal to 1 by 2. If one toss. Next, if 2 tosses are required in order to get the first head, then the probability which is equal to P2 which is equal to, suppose if we are using 2 toss which are required in order to get the first head, then P2 which is equal to 2 toss which is equal to 1 by 2 into 1 by 2 which is equal to 1 by 4. Suppose if 3 tosses are required to get first head, then P3 which is equal to 3 toss if it is required, then 1 by 2 into 1 by 2. Therefore, it is equal to 1 by 8. Next, if you want to find the entropy, how do we indicate the entropy? Which is HA is equal to summation I which is equal to 1 by n pi log 2 1 by pi. For this, after substituting 1 by 2 log 2 to the base 2 plus 1 by 4 log 4 to the base 2 plus 1 by 8 log 8 to the base 2 plus 1 by 16 log 16 to the base 2. So after simplifying the above, 1 by 2 I'll be getting 1 by 2, 2 divided by 2 square, 3 divided by 2 cube plus 4 divided by 2 to the power of 4. Finally, I'm getting near value as 2. So my answer is 2. In the multiple choice, they gave you the choice as 2, 3, 4, 5. By simplifying this question, then I'll be getting the answer as 2. My next question is the capacity of a binary symmetric channel which is indicated by BSC. They might ask you like the capacity of a BSC also. Binary symmetric channel with crossover probability. Given value for crossover probability is what? 0.5 is so we need to substitute the values over here. This is y1 of 0, y2, x2, p, y2, 1 minus p, 1 minus p, x1 of 0, that is x, y1 of 0, y. So given crossover probability in the question, already they gave you the crossover probability as what? 0.5. Therefore, P of x1 which is equal to 1 by 2, P of x2 which is equal to 1 by 2. Therefore, the channel capacity for BSC is C which is equal to log 2n minus summation j which is equal to 1 to 2 P of yk divided by xj log p yk divided by xj. After substituting to the above equation, I'll be getting log 2 to the base 2 p log p plus 1 minus p log of 1 minus p 1 plus 1 by 2 log 2 1 by 2 plus 1 by 2 log 1 by 2 to the base 2. After simplifying, I'll be getting 1 minus 1 by 2 minus 1 by 2 which is equal to 0. Therefore, my capacity which is equal to, the capacity of the channel is equal to 0. So this question they might ask you for 1 mark. So coming to the next question. A source alphabet consists of n symbol with the probability of the first 2 symbols being the same. Here our source encoder increases the probability of the first symbol by a small amount E after encoding the entropy of the source. The entropy of the source So given the multiple choice answers as the increases remains the same, increases only if n equal to decreases. Suppose if entropy is maximum when symbols are equal probable, that is when probability changes from equal to non-equal, hence the entropy decreases. So next question is based on the entropy of the source. Here, a memoryless source which emits n symbol each with a probability p, then the entropy of the source as a function. Generally, we are going to write the entropy h of m for the memoryless source as h of m n pi log to p.
ಇಲ್ಲ ಈಗ ಜಸ್ಟ್ 4:30.
Okay, sir.
8 questions for 20-25 minutes.
Here, entropy h of m increases as a function of log 2 n. Therefore,
ಆಗ್ತದೆ ಬರ್ತಿಲ್ವಾ?
okay, they gave you like increases, decreases as log n, increases as log n, increases as n log n. So my answer is increases because entropy h of m increases as a function of log to n. So next question is, a source generates three symbols with probability 0.25, 0.25, 0.50 with at a rate of 3000 symbols per second. Assuming independent generation of symbols, the most efficient source encoder would have average bit rate of, so they gave you the choices as 6000 bits per second, 4500 bits per second, 3000 bits per second, 1500 bits per second. Suppose if three symbols with probability of, already they gave you the probability as 0.25, 0.25 and 0.50 at the rate of what? 3000 symbols per second. Here entropy, which is indicated by H, which is equal to 0.25 log 1 by 0.25 to the base 2 plus 0.25 log 1 divided by 0.25 to the base 2 plus 0.5 log 1 by 0.5 to the base 2. After simplifying this, I'll be getting 0.25 into 2 plus 0.25 into 2 plus 0.5, which is equal to 1.5. Suppose if I want to know the rate of information, generally the rate of information which is equal to R equal R dot H, where R already they gave you the value as 3000 symbol per second. Therefore, R which is equal to 3000 into H, the entropy value is 1.5. Therefore, R which is equal to 4500 bits per second. So my answer is 4500 bits per second. So thank you for attending this part. So the next part will be continued by Professor Yaswanth. Over to Yaswanth sir. Thank you.
Good evening, students. So I'll be continuing the next topic with respect to the communication system. So that's what we are doing this business now, system communication. Okay, I'll taken some questions from the previous gate question paper. So I'll be checking that how they are going to ask with respect to this system communication. I'm planning to take like around 8 questions. We'll see that how the time passes and we'll discuss that how we are going to take that. Okay. As you know that as you are aware, the syllabus for this gate is with respect to digital communication. You can say that we are going to have what ECM. Just a minute. So we are going to have CM, DPCM, ASK, FSK, PSK. Just I'm writing here the syllabus before starting with the communication topics. Afterwards, we are having ML detector concept. Then we are having MAP. So apart from this, we are having bandwidth concept, SNR, DR, and also the ISA concept. So these were the topics we are going to have in the digital communication as per the GATE syllabus. So we'll see one by one with respect to these topics. So first question I have taken from the GATE previous paper. So that is what a sinusoidal signal, a sinusoidal message signal is converted to a PCM signal using a uniform quantizing. Okay, before starting with this question, I want to suggest some points with respect to the attempt to this GATE question. So you can say that first you better write down the given things. So after writing the given things, you just see that what are all the formulas we need to use for this. So as per that formula, you just try to attempt the question. So first you write the given, whatever they have given in the question. So after writing those parameters, then you move on to the formulas which are related to that. So afterwards, you can use the substitution with respect to this formula. So here the first question is a sinusoidal message signal is converted to a PCM signal using a uniform quantizer. So as you can see here, this is the question with respect to what? PCM. So this is a question with respect to what? PCM. So here they are telling that input signal we are going to give it to this PCM modulator is sinusoidal signal. So first you write down the given things. So here the thing is they have asked the question based on the PCM. So and also they are telling that input signal we need to take here is sinusoidal message signal. Sinusoidal message signal. So after taking that, so just see that whether they have given the uniform quantizer or non-uniform quantizer with respect to this technology. Since they have given a uniform quantizer, so we are going to apply the as usual formula for this. So meanwhile, they have asked here to find out the SNQR ratio. So here they are telling you to find out the SNQR ratio. So meanwhile, we need to see that what will be the minimum number of bits for this samples. Okay, sorry, the thing is 1 minute. So here they have given the what SNR. Here they have given the SNR. So just taking that SNQR is given by 40 dB. SNQR is given by 40 dB. Okay. So they are telling you to find out here. Find the minimum number of bits per sample that is needed to achieve the desired SNR ratio. So here the things are, they have telling that we need to consider the sinusoidal message signal and they have given here SNQR ratio that is 40 dB. So they are trying to, they are telling to find out the value for the number of bits per sample. That is we need to find out here. So actually you can say here, basically we are having two types of input we usually consider. So first type of input is normalized input. First type of input is normalized input. So for this, the formula will be, SNQR formula will be, SNQR dB is equal to 4.8 plus 6. So if they give you the question based on the normalized input, at that time we need to use this formula. At that time we need to use this formula. Suppose if you say that if they give you the input as sinusoidal signal, then at that time we need to use the SNQR formula as 1.76 plus 6. So since in the question they have told you to take the input signal as a sinusoidal signal, so we need to go with the second formula. So we need to go with the second formula. So they may ask you with respect to the first question also, it depends again. So here we are going for the second formula, that's what SNQRDB is equal to 1.76 plus 6. Okay, this SNQRDB they have given here as 40 dB, so that's what I am taking here. So after taking this 40 dB, so I need to find out number of bits per sample. Number of bits per sample. So that is N here. That is N here. So just a simple calculation here, simple manipulation we need to do. So 40 minus 1.76 divided by 6. So if you calculate this value, we are going to get like 6. We are going to get like above the 6. Actually, we are going to get above the 6. As we know that always we need to choose number of bits per sample greater than this n value. Why? Because see, like as per this concept, we are going to get greater than this 6. That means in order to represent all the sample with respect to this PCM technology, we need to go like higher bit value for this n. So we are going to get just simple calculation. You can say 40 minus 1.76 means I will be taking around like 2. So 38 by 6 means you can say here 38 by 6 is you are going to get greater than 6. You are going to get greater than 6. So based on this greater than 6 concept, so we are going to assign number of bits per sample as 7. We are going to assign number of bits per sample as 7. So since here we are getting more than 6 point value, so we are going to assign the number of bits per sample is 7. So the answer for this question is 7. So the answer for this question is 7. Okay, hope you have got the concept. So we will be moving on to the second problem. Okay, second problem is based on again the PCM technology, but they have asked it in somewhat different manner in this question. So a speech signal is sampled at 8 kilohertz. So again, I'll be writing down what are the given things they have provided in this question. So they are telling that the speech signal is sampled at 8 kilohertz. The speech signal is sampled at 8 kilohertz. And they are telling that for each sample, we are going to take 8 bits per sample. So we are going to take 8 bits per sample. See, here I am writing given things. So here they have given, we need to consider 8 kilohertz sample. So we are going to sample the speech signal at 8 kilohertz. Apart from that, they have given here, PCM is going to use 8 bits per sample. PCM is going to use 8 bits per sample. So based on that, so here we are going to have the bit rate as 64 kbps. So based on this concept, so here we are going to have the bit rate as RB. Bit rate is represented with the RB, which is given by what? 64 kbps. 64 kbps. So apart from this, they have given some more things here. As you can see here, they are telling that we need to go for the 4-level PAM. So instead of going for the 2-bit level, so here we are going for the 4-level PAM. Means with respect to this PAM, that is what pulse amplitude modulation. So we are going to have here 4 levels. We are going to have here 4 levels. So that also I have written here. So in the question they are telling us to find out the transmission bandwidth. So in the question they are telling us to find out the transmission bandwidth. So here I have written what are all the given things. So based on these given things, we are going to use the formula which are related to this. So finally we are going to find the unknown bandwidth. So here they are telling that we need to find out the minimum bandwidth required for the transmission. Minimum bandwidth required for the transmission. So one thing you need to remember here. So here the symbol period is not equal to bit period. That means it is directly not equal to bit period. Since here we are using the 4-level PAM, since here we are using the 4-level PAM, you can say the relationship between the symbol period and the bit period is given by TS is equal to TE log 2. See, the thing is first we need to find out the relationship between the symbol period and the bit period. Symbol period and the bit period. Why? Because at last, in order to find out the transmission bandwidth, in order to find out the transmission bandwidth, so we need to use here what? 1 by 2s, 1 by 2ts, or you can write it as rs by 2. So this is the transmission bandwidth formula for the given symbol. So if you are using the 4-level PAM, at that time you need to use the Bt is equal to rs by 2. Bt is equal to rs by 2. Suppose if they are given like only 2-level PAM, at that time this Bt can be equal to what? Rs by 2 equal to Rb by 2. Why? Because this Rs is equal to Rb then. this RS is equal to RB there. Why? Because zeros and ones only we are going to use in order to represent these levels. So symbol bit is equal to what? Symbol value will be what? Equal to bit value. So at that time, if you are saying only 2-level PAM, if you are saying 2-level PAM, at that time we are going to use this band. But since they are given here more than 2-level, that is 4-level PAM. So the formula we are going to use here is TS is equal to TB log 2M, and the BT is equal to what? 1 by 2 TS is equal to RS by 2. So these are the things we are going to use here. These formulas we are going to use in order to finally obtain the BT. Okay, we'll see that what are all the given things they have given here. So just I'm writing the first formula. So that is what TS is equal to TB log M, log base to M. So here I will be writing this as TB as 1 by RB. So here I will be writing this as TB as 1 by RB. So 1 by RB log 2M. So as you can see here, they have given you the bit rate. Bit rate is nothing but number of bits per sample. So number of bits per sample. So the total bit rate PS. So the total bit rate for this PAM signal transmission is 4-level PAM signal transmission is what? 64 kbps. 64 kbps. So this one I have taken here. This is what 1 by RB is equal to what? 1 by 64 kbps. So this into, since in the question they have told for the 4-level PAM, so here we are going substitution as log to 4. So here we are going to obtain the TS. So this TS is given by, so just do the substitution. That's what calculate this thing. So 64. Just a minute. So 2 divided by 64 kbps. So this is what? 1 by 32 kbps. Okay, log 4 is nothing but 2 only. So 2 divided by 64 kbps is nothing but 1 by 32 kbps. So this is the what? In order to find out the symbol pair. So this is the formula we are going to use in order to find out the symbol pair. So next, finally we need to find out what here? Bandwidth. So bandwidth is given by what? So 1 by 2 TS. Bandwidth is given by what? 1 by 2 TS. So we will find out that bandwidth now. Transmission bandwidth. Okay, so this transmission bandwidth is given by what? 1 by 2s. So I'll be using, I'm not going to use this formula, so I'll be using this 1 by 2s formula. So 1 divided by 2 into TS is nothing but what? Again 1 divided by 32 kbps. So 2 ones are 16. So here we are going to get 16 kbps. So the answer will be what? It is what? 16 kilos. Again, here we are representing that in terms of bandwidth. So here the answer we are going to get as 16 kilos. Okay, this is the second question with respect to the PCM, you can say. So the answer will be what? 16 kilohertz. So one thing you need to remember here is the symbol period is not equal to the time bit period. So why? Because here we are using the 4-level time. Okay, we will be moving on to the third question. So in this third question, we are going to take based on this DPCM. So here the question is like this. So which one of these following statements about the differential pulse code modulation is true? So the third question is, which one of the following statements about differential pulse code modulation is true? So just here they have given 4 different statements. So we need to take the statement which is true according to this DPCM. So you refer the first statement here, the sum of message signal sample with its prediction is quantized. The sum of message signal is simple is its prediction is quantized. So here we are going to take the sum of this message signal sample and then we are going to predict it. So that is not the case. Why? Because, so I will brief out the things here. See, in the PCM, we are going to consider the sample directly. Afterwards, we are going to quantize it and then we are going to encode it. In the PCM technology, first we are going to sample the input signal, then we are going to quantize it. Afterwards, we are going to encode it. So that is the PCM. So here's in the question they have asked the DPCM. So as the name itself tells here, DPCM is nothing but the differential pulse code modulation. So this is what differential pulse code modulation. So here we are going to take the difference between the successive samples. So we are going to take the difference between the two samples. Suppose if I say that my samples will be like this. After taking the input signal, I'll be having the samples like this. So we are going to take the difference of these two samples, and that difference sample, the difference value, we are going to quantize it. Instead of quantizing the sample as it is, so here we are going to quantize the difference value. Here we are going to quantize the difference value. So that is what we are going to take the difference value, then we are going to quantize it, then we are going to encode it. The thing is, why we are going for this means in order to consume the less bandwidth. In order to consume the less bandwidth, so we are going to take the highest Nyquist rate, and we are going to quantize its difference value, and then we are going to encode it. So in this way, we are going to send the DPCM signal. So in the question, now we need to check that. In the answers, we need to check that. So how we are going to do the things with respect to this DPCM. So sum of message signal sample with its prediction is quantized. So there is not true with respect to this. The message signal sample is directly quantized. So this is also not true. Why? Because this is with respect to the PCM concept. So this is also not true for this DPCM. Okay, if you take the third question, the difference of the message signal sample and a random signal. So actually we are not going to take any random signal here. So we are not going to take any random signal here. So third one is also a false one. Okay, if we go for the fourth one, the difference of a message signal sample, so the difference of a message signal sample with its prediction is quantized. So this will be the correct answer for this DPCM. So in this DPCM, we are going to consider the difference of the message signal sample. So that's what I told you. We are going to take the difference value. So after taking this difference value, we are going to take its prediction also. It is its prediction also. So we are going to take both of it, and we are going to quantize it. We are going to take both of this value and then we are going to quantize it. So in this way, we are going to do this DPCM. So that's why I can say that fourth statement will be true with respect to this question. Fourth statement will be true with respect to this question. Okay, we'll move on to the next concept. So here we have given somewhat summary. So this is the difference between the PCM and the DPCM. So you can see here number of bits per sample, number of levels, how the one technology is different from the other technology. So basically these are the digital modulation technique. So how this PCM is different from the DPCM. So you can see this comparison, parameter wise comparison. Like suppose you consider bit duration. So here it is having very less in the PCM, but DPCM it is having less. Similarly, steps are both are fixed. And if you come to the bandwidth, so you can say that bandwidth will have highest with respect to this PCM, and it will be less compared to this PCM. In this DPCM, complexity is complex with respect to PCM, whereas in the DPCM it will be simple. It will be very simple. So if you consider feedback, so there is no feedback for this PCM, and if you consider the DPCM, so there will be feedbacks exist. So this is just a comparison between these two pulse digital modulation. So how these two technologies differ. Okay, next we go for the next problem. So in this problem, actually we are going to take a digital modulation technique. So I'll read the question now. So in binary frequency shift keying, so here they are telling that we need to take the FSK modulation technique. So here the binary frequency shift keying. For this binary frequency shift keying, they have given two signals in order to represent the bit values. So one frequency signal is given by U of t. So phi cos 20,000 pi t, 20,000 pi t. So next U1 of t is equal to what? Phi cos 22,000 pi t. So in order to represent these bits in the FSK modulation, we are going to use the two carriers. We are going to use the two carriers in order to represent this bit 0 and the bit 1. Okay. So meanwhile, they are telling that this U of t and U1 of t are 0 outside the interval, 0 less than or equal to t, less than or equal to time period of the bit, that is the capital T. So that means what? You can say that the bit will be the bit value will be lies in this range. The bit value will be lies in this range. So outside that, these both signal will be 0. Outside that, this both signal will be 0. So here they are telling that you need to consider one matched filter. So in that matched filter, we need to find out what will be the smallest positive value of t required in order to have these two signals uncorrelated. So we need to use matched filter. So as you can see here, both the concepts came here. So one is modulation concept, FSK modulation concept, and one more is matched filter concept. So here the thing is, we need to choose the smallest positive value of the time t. So that will give the uncorrelation between the signal U1 and U0 and the U1. So here we need to choose the smallest positive value of the t. So that will give the uncorrelation between the U0 of t and the U1 of t. So that time period we need to find out. So from this options, we need to find out time period in which these two signals are uncorrelated with respect to this matched filter. So that we need to find out here. Okay, actually, in order to have this concept, so we are going to use the orthogonal concept here. So actually, in order to have uncorrelation between these two signals, we need to consider this statement. So if the two signals are orthogonal, then it has to satisfy these conditions. Then only we are going to say that. So it is having what uncorrelation between the two signals. So we need to have this condition in order to have uncorrelation between these two signals. So F1 frequency is the one of the signal component. F0 frequency is the other signal component. So here the n gives you the number of values. So how much it is differable with respect to these two frequencies. Okay. So first we'll calculate this F1 and F2, F1 and F0. So F0 is given by what? F0 is given by what? 2 pi F0 is equal to 20,000 pi. So here I am going to get F0 is equal to 10k. F0 is equal to 10k. So just see here. So here I am taking this first U0 of t. So this is nothing but 2 pi F0. This is nothing but 2 pi F0. So this 2 pi F0 is equal to 20,000 pi. So that's what I have taken, and I have found out the value for this F0. I have found out the value for this F0. So next similarly I will be taking F1 frequency component. Similarly I will be taking what? F1 frequency component. So here you can see here this is nothing but 2 pi F1. This is nothing but 2 pi F1. So this 2 pi F1 is what? 22,000 pi. 22,000 pi. So based on this you can say that F1 we are going to get here as 11 kilohertz. 11 kilohertz. See, in order to have the uncorrelation, between these two signals, we need to consider the orthogonal condition. So we are going to say that two signals are orthogonal. Only those two frequencies will satisfy these conditions. Only those two frequencies will satisfy this condition. So that's why we are taking here. So after taking that, so we need to choose the minimum value of the n. So minimum value of the n, so that we are going to get the this orthogonality. So minimum value of the n we need to choose so that we are going to get this orthogonality. So here we are going to choose as n is equal to 1. So we can go for the 2, 3, 4 also. But here they are telling that minimum time they are asking. In the question they are telling that minimum time. So that's why here we are choosing the n value as 1. That's why here we are choosing the n value as 1. So here you can say that F1 minus F0 is equal to 1 by 2t. So F1 is here 11k minus 10k is equal to 1 by 2. So the time required in order to have this uncorrelation between these two signals is 1 divided by 2 into 1k. See, the thing is I have taken the difference here. 11k minus 10k is nothing but 1k. So just I'm shifting these two values over here. So t is equal to what? 1 by 2 into 1k. So t is equal to, we can say that 1 by 0.5 millisecond. 0.5 millisecond. So 1 by 2 is nothing but 0.5. So we are having kilo component at the denominator. If you take at the numerator here, so here we are going to get the 0.5 millisecond. So the answer will be what? 0.5 millisecond. So we are going to consider the orthogonality concept in order to have the uncorrelation between these two signals. In order to have the uncorrelation between these two samples. Okay, next question I'm going to take now. So that is based on the QAM. Actually, based on the QAM also they can ask you in the question. So here the fifth question is based on the QAM. Okay, just I'll be writing down the given things here. So based on that given things, we'll try to find out that how we are going to obtain the unknown quantity here. So in the question they are telling that we need to consider the ideal bandpass channel, which is having 500 to 2000 hertz. So here they are telling that the bandpass channel is there, so that is having from 500 to 2000 hertz. They are telling that one channel is there, that channel is having 500 hertz to 2000 hertz. 500 hertz to 2000 hertz. Okay, that they have given. Meanwhile, you can say that this is the bandwidth of the channel. So this is the bandwidth of the channel they have given in the question. So bandwidth of the channel, this is the transmission bandwidth of the channel. They have given the frequency range of the channel. So that means we can say that it's a bandwidth for the channel. That means you can say that it's a bandwidth for the channel. Okay, channel bandwidth is given by 1500 hertz. So apart from that, they have given the bit rate. So this bit rate is nothing but what? RB is given by 4800 bits per second. Okay. So meanwhile, they are telling that we need to go for the 16 QAM. We need to go for the 16 level QAM. So quadrature amplitude multiplexing is the technology, modulation technology. So here we are going to use the 16 level. Here the M value will be what? M array QAM. Here the M value will be what? 16 level. So meanwhile, they are telling that we need to find out the roll off factor. So what will be the roll off factor of this pulse if you consider the riser cosine spectrum? If you consider the riser cosine spectrum, so what will be the roll off factor for this? What will be the roll off factor for this? So after writing down this given things, so just note down here that what are the formula we are required for this. So we need to know the value of this RS. So we need to know the value of this RS. See, again here they have not given that symbol period is equal to bit period. So symbol period is varying from the bit period. Since we are using here M array QAM. So since we are using here M array QAM, so this is what bit rate. Symbol rate is not equal to directly bit rate. So symbol rate is not equal to directly bit rate. So that's why we are going to use this formula. RS is equal to what? RB by log 2m. So just already I have used this formula. You can say that TS is equal to what? TB log 2m. So the same formula here we have taken in terms of what? Bit rate. Symbol rate and the bit rate. Previously we have taken in terms of symbol width and the bit width. So here we have taken the same formula in terms of symbol rate and the bit rate. So this formula we have required. So since the roll off factor formula will take the help of this symbol period. So next, in order to find out this roll off factor, we are going to use this transmission bit formula, transmission bandwidth formula, which is given by BT is equal to what? RS into 1 plus alpha. So here we are going to use these two formulas in order to find out the what? Roll off factor. In order to find out the roll off factor. So we'll consider it now this formula. So RS I need to find out first. In the question they are telling that we need to take the bit rate as 4800 and here they have given us M level as 16. So from this you can find out the value of this RS. RS is equal to what? 4800 divided by log 2 16 is nothing but 4. So here we are going to get the symbol rate as 1200 symbols per second. 1200 symbols per second. So this is the RS value. So by using this RS value, so we are going to find out the roll off factor. So transmission bandwidth is given by BT is equal to RS into 1 plus alpha. So BT here is how much? 1500. 2000 minus 500 is nothing but that is the bandwidth of the channel, transmission bandwidth of the channel. So which is what? 1500. So that equal to RS is 1200. So 1 plus alpha. 1 plus alpha. So if you take this 1500 minus 1200, I am going to have 1 plus alpha here. Sorry, just a minute. It actually will be division. So this will be what? Division. So 1500 by 1200. So it will be what? Approximately how much we are going to get here? So 1500 by 1200 means we are going to get here 0 0 get cancelled. 4s are 5s are 5 by 4. 5 by 4 means 1.25. So 1.25 is equal to 1 plus alpha. 1.25 is equal to 1 plus alpha. So 1.25 minus 1 is equal to alpha, which will give you the role of factor. So the role of factor is given by alpha is equal to 0.25. Alpha is equal to 0.25. So the thing is, first you write down the given things. So first you understand the question and write down the given things. Then after taking down those things, you can go for the formula. So then afterwards you can find out the answer. Okay, I will be discussing the last problem with respect to last question from this digital communication. So meanwhile, you can refer these topics. We are going to share this with the YouTube. Okay, the next question will be what? For a bit rate of 8 kilo bps, for a bit rate of 8 kilo bits per second, the best possible values of the transmitted frequency in a coherent binary FSK system are what? So they are asking us to find out the best possible values of the transmitted frequency in a coherent binary FSK system. For a bit rate of 8 kilobits per second, what will be the best possible values of transmitted frequency in a coherent binary FSK system? So they have given the 4 options as we know here. So the thing is, always we need to choose the transmitted frequency. It should be like multiples of the given bit rate. So always we need to choose the frequency. So the best possible values for this transmitted frequency, what? It should be in terms of multiples of this given bit rate. Multiples of this given bit rate. So as we know that FSK requires 2 carrier signal. FSK requires 2 carrier signal. So for these 2 carrier signals, we need to choose the frequency. We need to choose its frequency. So that should be what? Multiples of this bit rates. Multiples of this bit rates. So that is the best one. So others also we can able to select, but the best ones are the multiples of this 8 kilobits per second. 8 kilobits per second. So if you consider the first one, so as you can see whether it is what whether it is a multiples of 8 kilobits per sample or not, you need to consider both the frequency. So anyhow you can see here, the first frequency, it's a multiples of this 8 kilobits per second. It's a multiples of 8 kilobits per second. But if you consider this 20 kilohertz, it's not. So this first one is not possible. So both the frequency we need to choose the best one. With respect to this, both the frequency we need to choose the best one. Okay, similarly go for the second option. So here also, as you can see, first one is not multiples of this bit rate. So but second one is multiples of this bit rate. So second is also not possible. So if you go for the third option, so in the third option you can see both are not possible. Why? Because it's not multiples of the 8 kilobits per sample. Okay, if you go for the fourth option, so you can see that these 32 kilohertz and also this 40 kilohertz, both are the multiples of this bit rate. Both are the multiples of this 8 kilobits per sample bit rate. So the option for this sixth question is, you can say the D. The option for this sixth question is, you can say the D. Okay, these are the questions. You can say that some of the questions based on this digital communications. Okay, again, they will ask other than this also. Why? Because as we know that that's just sample questions. So when they ask related to this also, they may slightly alter this and they may ask that also. Okay, so you can say that all the for your GATE exams. So I'll be ending the session. So you can watch our video in the YouTube. So meanwhile you can ask us any doubt if you want with respect to this comments section. Okay, thank you for the session. So I'll be ending this session. So this is based on digital communication. Okay, thank you once again. All the best for the GATE exams.